Welcome to this recorded talk on virtual ASICs. I'm Chaya and I'm joined here by Daniel, and we are going to present our work on generalized proof of stake mining in cryptocurrencies, which is joint work with Claudio and Aviv.
All right, so let's start with proof of work, or how to waste energy. So starting point of our work is proof of work, and more specifically, the block lottery it provides. So the idea is you invest some work, and by doing so, you actually participate in this lottery. And if you win, you get this certificate. In Bitcoin, it's this nonce, which allows you then to produce a block. And so what we know about this lottery is if 51% of all computing power is honest, then this gives us a nice blockchain. So here again, you can see the properties we achieve, right? Invest this work. This is essentially solving crypto puzzles. Your winning probability essentially depends on how much computational power you have. And this is used in Bitcoin, as I said. The drawback of it is it has a rather high energy cost. So on the right, you can see a picture of one of these mining farms, specialized computing hardware, which is used in this case to mine Bitcoins. This is a problem for the environment. So the question is, can we do better?
And a greener alternative to achieve consensus is what is called proof of stake, where to participate in the lottery, parties have stake in the system instead of having to invest work to participate. And analogous to the winning probability being proportional to the amount of work invested in proof of work, here in proof of stake, the probability that a party wins a lottery is proportional to the amount of stake that they own in the system. And the advantage here is that unlike proof of work that is used in Bitcoin, this has low energy cost and is therefore much greener. However, there are also several advantages to proof of work that use physical ASICs, one of which is the following, which is about borrowing money. In proof of stake, an attacker can borrow money from a participant in the system and then mess up the system, thereby leaving it completely useless, and then return the money. And now the returned money is practically useless to the lender because the system is not good anymore. And this is stemming from the fact that stake plays the dual role of both the currency in the system and the lottery power, which determines who has more say in the lottery. In proof of work, on the other hand, which uses physical ASICs, owners use these application-specific circuits that, as it suggests, is specifically designed for this purpose and therefore useless for any other purpose. This means that owners are heavily invested in the cryptocurrency and retain control of borrowed equipment. There are also problems like nothing at stake attacks in proof of stake based systems, which are not so in proof of work based systems. So the question we ask is, can we get the advantages of these ASIC based systems without burning down the planet?
And that is what our work is about. So we actually start with the physical ASICs on the next slide. So here you can see on the right, this is actually one of these ASICs used for, I think, Bitcoin mining. And I mean, essentially, this allows you to participate in the proof of work lottery. It has a mining rate. Essentially, what you normally look at is how many hashes can you compute per second. And such ASICs, of course, require power, so you pay electricity costs. And normally you can buy those ASICs anywhere. I mean, there are specialized companies making them. So the idea now is to port those properties of this actual ASIC into the world of proof of stake. So what we can do here, we want that the virtual ASIC allows parties to participate in the lottery. There needs to be a way to acquire ASICs on-chain. And then we also want to model the power requirement by having virtual power. And of course, rent or even maintenance cost for such ASICs should be incorporated. So there are two things we have to look at here. One, Chaya will talk first about, is the virtual ASIC lottery, and then later on we look at how you can actually buy ASICs using an on-chain auction.
So coming to the virtual ASIC lottery, which essentially gives us the advantages of proof of stake and the advantages of physical ASICs without the disadvantages. So we have several properties of a virtual ASIC. These are basically publicly known properties associated with a virtual ASIC that is on the blockchain, which is a mining rate of a virtual ASIC and the degradation rate of the mining rate of an ASIC, whether or not an ASIC is powered to be used in the lottery, and certain ownership information that associates an ASIC with a participant in the protocol. So these are all attributes that are on-chain. And now to get a lottery that is based on virtual ASIC power, we can borrow similar templates that we saw earlier from proof of work and proof of stake, which is essentially a lottery, and participants participate by investing the virtual ASIC mining rate that they own. And if they win, they are allowed to publish a block that goes onto the blockchain. And in the paper, we elaborate on how to use the Ouroboros browse template to obtain a consensus based on this virtual ASIC lottery.
We will actually talk about the lottery a bit later when we talk about the design space we have. But first, let's look at how we can acquire ASICs on-chain using an auction. So the basic idea of the auction we describe in our paper is a two-stage auction. So we have a bidding phase where parties can enter their bids and a decision phase. The auction we consider in particular here is a K+1 price auction. That means you have K winner and they pay the bid of the K+1 highest bid. That's a generalization of a victory auction. So the properties of this auction, right? The things we actually need and want to have. First of all, bids need to be confidential. Bids should be independent, so it cannot be that a bad guy comes and says, "Oh, I bid whatever Alice has bid, but +1." Of course, in the decision phase, bids need to be publicly verifiable. We also have a problem here, right? We want to do an on-chain auction, so censorship might be an issue, because this is an auction which talks about virtual ASICs. So the people who own virtual ASICs might be inclined to censor bits of other people, such that their ASICs kind of retain value. So we need to deal with that as well. And finally, of course, the auction must be binding. Now, in a physical auction, that's pretty easy, right? You have laws which do that. But here on-chain, we need to ensure that if someone presents a valid bid in the decision phase, they can't just move away their money. So here you see an overview on our protocol. It has actually 3 parts. So first, in the bidding phase, what we do is we start off with escrow payment. The idea is, in order to make bids this binding, we let people pay into an escrow account. And we do that using a shielded transaction. This ensures that the bids are hidden. And then the parties actually put their signed bids together with information on the payment to the escrow account into what we call an all-or-nothing broadcast channel. We will talk about this in a moment. But then at the end, once this channel announces all the bids, what we do is, we just take the first valid bids, and the validity here depends on whether the party made the correct payment to the escrow account, and we can announce them as winners. And then, of course, because we have already a chain which we assume has some sort of payment system on top of it, we can transfer the amounts back to people. So as a winner, you get paid out the difference, and if you lost, you just get back your money. So now Chaya will talk about this all-or-nothing broadcast channel.
So our all-or-nothing channel is a building block for the auction. So let's look at how we construct an all-or-nothing broadcast. So the functionality we want is simply the following. Parties enter inputs into the channel, and there is a certain amount of delay period And at the end of the delay, people should be able to read out the messages from the channel. So what can the adversary do? Here, the adversary has the following power. Either they can prevent the output of all the messages, or all of the messages are delivered. That is why we call it an all or nothing channel, because either all the messages are output or none of them are. So how do we achieve such a broadcast channel with the all or nothing property? The idea is to use threshold cryptography. So in threshold crypto, keys are shared and many parties own each share of the key. And then many parties can come together, and when a certain number of parties come together, things can be recovered and messages can be decrypted. The problem here in our setting is that in the blockchain setting, any sort of setup procedure becomes infeasible because we want participants to dynamically join the protocol. So what we need here is a threshold encryption with an ad hoc property where participants can join without having to participate in an earlier setup phase. So what is this threshold encryption with an ad hoc property? It is the following, where each miner comes and publishes a public key in the first phase of the construction of the channel. And once a certain number of public keys have been published, to encrypt, we use this ad hoc threshold encryption. And at the beginning of the decryption phase, each miner reveals the secret key corresponding to the public key that they published earlier in the first phase. And once T+1 secret keys have been published on the chain, decryption becomes possible publicly. So how do we use this broadcast channel for the auction? It follows the template that we saw earlier. And in particular, in the bidding phase, parties simply enter their signed bits into this all or nothing broadcast channel. Remember, an escrow payment has already been done earlier, and the bid is tied to a particular transaction. And now after a certain amount of delay, keys are released and these bids can be decrypted publicly, and everybody can check who won this auction. So do we get all the properties that we wanted earlier of the auction? So bid confidentiality we get from shielded transactions of the escrow payment and from the properties of our all or nothing channel. We get bid independence from the properties of our AON channel. We have public verifiability because everybody can decrypt on the blockchain and determine the winner. Censorship resilience is given by the all or nothing property of our channel, where the adversary can either stop all bids or all of them are published. And we get binding because of the escrow payment even before bids are entered into the channel.
All right, so finally, let's talk about the design space we have here. And for this, first of all, again, reminder here that the lottery we achieve with the ASICs is secure as long as a majority of ASICs is in honest hands. So similar to proof of stake or proof of work, you need this honest majority. So let's look at the different knobs and switches which we can use to actually design virtual ASICs. But oh yeah, true. So first, before we even go to them, let's talk actually about the power. Forgot about that. So in our setting here, especially with our consensus protocol, we divide time into epochs. And so at some point you will buy your ASIC, and at that point you have it actually. So later on, if you want to use it, you actually should power it. And so in order to actually buy power, what you need to do is you need to go and buy power on chain. And that means your ASIC is now powered for the following epoch. It's not powered immediately, because if you buy power, right, there's the issue at what point is it confirmed. And so there needs to be a slight delay in between. And thus you need to buy power early enough to have your ASIC powered in a certain epoch. But once it's powered, you can use it for the ASIC lottery. Now, as you can see here in the picture, this ASIC would be powered for the middle epoch here. If you now want to also have it powered in the last epoch, of course, then you would have to buy power again, as you can see here. So this brings me to the next part. We already mentioned that is mining rate and degradation. So each ASIC has an initial mining rate assigned to it. That's the mining rate it has after the auction, once you get it. And the mining rate is constant for each epoch. Again, the idea is kind of that we have a certain consistency per epoch. And then at the end of the epoch, degradation can happen. And here you have a choice. Degradation can be different depending on whether the ASIC was powered or not. The idea here essentially is that we can incentivize people to actually power their ASIC, although that is costly, by just making the degradation less severe than if the ASIC is unpowered. So this brings us now to the knobs and switches. So first of all, we can talk about ASICs, the supply and the costs. So here the question is, for instance, is your ASIC supply limited, so capped? Or do we have an unbounded supply of ASICs? So every epoch we sell off a bunch of them? Or do we say, no, this is not good. We let them degrade and we only auction off kind of the ASIC power which got lost. Then we can also talk about power itself, like the virtual electricity. Again, question is supply. Do we have unbounded amount of electricity? What is the cost? Is it constant, or is there some sort of supply or demand mechanism built in? And finally, we have degradation. So we can decide whether ASICs should degrade or not. And here's an example. So you can actually model proof of stake as a virtual ASIC, and the idea is quite simple. ASICs are kind of stake. I mean, you can think of them as a special token which allows you to participate in proof of stake. You can buy them. There is some mechanism, potentially an auction. Power is for free, so you don't have to pay for participating in the lottery as it is in proof of stake. Degradation itself is optional, because if you want to have it, it can be quite a nice tool to actually enforce inflation. So the thing is if you remember, right, in Bitcoin, you don't really have an inflation because the coin supply is actually capped. But here in this ASIC model, what you can do is you can either degrade existing ASICs and have new ASICs brought in, or you could also have no degradation, but you just sell off more powerful ASICs. So this way you can actually model proof of stake. There's also another special case, and that is proof of burn, the idea of actually burning money to participate in the lottery. So here what we do is we say, well, everyone can have as many ASICs as they like. However, it costs you power to use your ASICs. There is no degradation as ASICs are for free, so that makes no sense. And so now what you have is you have a lottery where parties need to burn money to actually participate and create blocks. And that is what is known as a proof of burn. And yeah.
We are going to conclude here. Thank you for joining us. And hopefully one of us is going to be on the chat to take questions. And you can find more details about this on the ePrint report 2020-791. Thank you again.